Hello, everybody. Wait a couple more minutes for everybody to join in. Okay, so tonight's topic, we are starting chapter 9, and this is going to be tonight's lecture is about stress transformation. People are still filtering in. Before we start tonight, though, in case you haven't checked on Blackboard, but I did grade all the midterms over the weekend. So you should be able to go to Blackboard and see your score for the midterm 2. And you also, somebody please correct me if this is wrong, but you should be able to get into Blackboard or Respondus or one of those apps and see where I have annotated every person's midterm. So every point that you missed off of the midterm should have an explanation that I filled in for your tests.
Professor Pratt.
Yes.
So I did go to Respondus to look at like my score and like the points, like how many points I got in each question, but I didn't see like any annotations on like where I lost points. So
Really?
I don't know, where were they?
Well, there's a text box that I had that I used the text box. So it wasn't on the PDFs of the work that you turned in. The PDFs of the work that you turned in, I gave a 0 for everybody because that's not where I was giving the points.
Okay.
But it's on the actual Respondus midterm 2 where you filled in the text boxes, and then there was a text box for me to use for grading. So that's where your grade is, and that's where all your annotation is.
Oh. Yeah, I didn't see I didn't see like any of the annotations, but
I think you need to use Respondus to go check it out.
I mean I used Respondus to like check out the points, but I didn't see a text box. But
Did you try clicking on the points?
Let's do it this way. Did anybody see what I had typed in and as to why points were missing? Has anybody found that?
No, I haven't, but what I've seen is once you click on the points, it takes you to another window. But since I'm not on Respondus right now, I can only, it won't let me access the document.
Professor?
Yes?
I just got here. I'm a little confused with what you guys are talking about.
I graded the midterms over the weekend.
Okay.
And you should be able to go to Respondus or Blackboard and see your midterm score. And what we're talking about is you should be able to go into it and see the annotation that I did. I spent many, many hours on Sunday typing in exactly where all of the points were that were missed on the midterms. So let's work on that. There's got to be a way for you guys to access your test and see those annotations. Ryan, you had asked what was the class average. The class average was about 32.5 or so. Yes, I believe you have to go through Respondus to see what I had written. But yeah, we need to figure that out because, like I said, I spent a lot of time. I wasn't planning on covering the test tonight because I had spent so much time on each individual's test typing out exactly what you missed and why I took off points. There's a curve for the whole grade will be curved based on the final results of the whole class. So there may be a curve, but I just don't know what the curve's going to be until all the data is in, which includes the final for Tanqing.
Professor, is it okay if I ask something?
Yes, of course.
So I was looking at the midterm 2 hand calculation work that you graded. It says 0. Are we supposed to get a score for that?
No, you're not. The hand calculation that you turned in for the midterm 2 is everybody got a 0 because that's not what I graded. I
Okay.
used the hand calculation most definitely to give everybody the best possible grade because there was a lot of work in there that I could pick out and give most everybody at least partial credit if they didn't get the right answer. But the grade is on the respondus test, not on the hand calculation that you sent in.
Okay, so we would have just open responders. Okay. All right, thank you.
All right, so do you think if we're a little above the average for both tests, we are fine? Yasmin, you can email me offline or you can catch me during the office hour, like next Wednesday, and we can go over your scores specifically. I don't want to make any generalizations about if you're fine or if you're not fine or even what fine means over this forum. So not punting down the road, but if you get a hold of me privately, we can discuss exactly where you are. And to Juan, is the final going to be similar to the midterms? Yes, it is. It's going to be exactly like the midterms, only with an additional problem because you have 2 hours to solve. Chad, the final is worth 50 points, not 100. It will be worth 50, same as the midterms. It's just weighted heavier for your final grade. So the final exam, if you look at your syllabus, is worth 30% of your grade. Each midterm was worth 20% of your grade. Okay, everybody okay so far with the midterms? And hopefully we can figure out how to, you can see your exact scores. Were you guys able to at least see what your score was for the midterm, but you can't see what I typed in?
I was able to see my score and like how many points I got in each question, but not the comments that you wrote.
Okay. Okay. I'll try to figure that out. Okay. Thank you.
Thank you.
Okay. So tonight is actually a pretty big topic, and we're going to have to start moving forward with it. So I'm going to start tonight's lecture. And tonight's lecture is about stress transformation. This is a pretty big subject for this class. And so without further ado, if we look at a cube of material out of a structural member, so this is just like a steel I-beam or a wood glulam or whatever, any kind of a structural member, I can grab a little cube of material and pluck it out of that member and just look at it as a little element. Okay, Kira, okay, thank you, Kyle. There we go. And so in 3 dimensions, there are 3 independent normal stresses in the Y, in the Z, and the X direction. And so we use the subscripts as follows. This is going to be our sign convention. In the y-axis, a normal stress is Y, in the z-axis C, and the x-axis X. That's pretty self-explanatory. And what I'm not showing is stresses on the sides not shown are equal and opposite. So in other words, this Y, normal stress Y, there's an opposite normal stress y on the other side to exactly balance it, and that's the same in all directions. But just for clarity, I'm not showing those. They're not independent. They're the same as these guys. We also have 3 independent shearing stresses, as you can see here. And we have some equilibriums here. So tau xy here is equal and opposite to tau yx here. Tau yz is equal and opposite to tau zy, and so on and so forth. So there's really only 3 independent shear stresses because through equilibrium, the other ones have to balance these. Okay, so on each one of these shear subscripts, you have to have a sign convention that tells you exactly what direction it's going. So the way that we've established this is the first stress subscript notes the direction of the normal. So right here, tau yx, y is the normal. So that tells you which face the shear stress is on, and then the x tells you in what direction the shear stress is going. So tau yx is on the y face, and the stress is going in the x direction. Tau yz is on the y face in the z direction, and so on and so forth. So you can see each one of these follows that. This shearing stress here is on the x face pointing in the y direction. So if we limit our discussion to 2 dimensions, I want to look at just planar stress transformation. So what's in a single plane is just going to be the normal in the y, the normal in the x, and tau xy. And again, on the other 2 faces you can't see is the equal and opposite. So if I take this cube and I make a slice right through the middle there, and I look straight down, this is what I see. So this is looking straight down, and this is my y direction, this is my x direction, and this is my stress, in the normal stress in the x direction. We place sigma x in the x direction. We have sigma x going in the opposite direction over here. So again, these are not independent, they are equal and opposite. We can add sigma y in the y direction. This is the positive. And sigma y is independent of sigma x. And of course, we sum the forces. Sigma y is down in the equal and opposite direction. And if we have shear acting on the element, then we add it in the xy direction. So again, xy, this is on the x, on the face that is normal to x, going in the y direction. So this is positive. And please make a note of this, that this direction as drawn is a positive shear. If the arrow is going in the other direction, then it would be a negative shear. By summing forces in the y direction, we find by equilibrium that tau xy acts in the opposite face in the opposite direction. So in other words, you sum all the forces up and down, sigma y and sigma y cancel each other. You have to have a tau xy in the opposite direction to cancel this tau xy to equal 0. So we place tau xy in the minus y direction. Summing forces about the corner of the red circle, the sigma x's cancel each other, the sigma y's cancel each other, but notice you have this tau xy with a moment arm of the width of my cube that is not canceled by this shearing stress. This stress has no moment arm, but this one does. So I have to have something that balances this tau xy. So I have to have tau yx with the same moment arm about this point here to cancel this one. And so what that means, basically what we're concluding, is that tau xy equals tau yx. All the shearing stresses are equal in magnitude. Okay, let me stop for a second, make sure I'm not going too fast. Do I have any questions about this so far? Okay, so this is all the possible stresses in this coordinate system. So any stress in any other direction would just be a combination of these stresses here. Sigma y, sigma x, and tau xy, all three of these are independent. So like I said, all the shears are equal in magnitude, but the shear is independent of the normal in the x direction, which is normal or independent of the normal in the y direction. So we really have three independent stresses in this coordinate system, and that completely describes in the 2D world everything happening with this element. Any questions about that? Okay, so stress transformation. What this means is we may know what the stresses are in the XY coordinate system. But what we need to be able to do is if I rotate this coordinate system to any angle above or below the x-axis, then this whole unit is going to rotate. We need to be able to solve for the normal stresses and the shear on some other reference system, x prime, y prime. So we need a way to transform the stresses in the xy coordinate system to the x prime, y prime coordinate system, like so. So if I rotate this whole coordinate system by some angle theta, then I have a whole new set of stresses. I have sigma x prime, I have sigma y prime, and tau yx or tau xy prime. So these stresses are related to these stresses, but they're different. And they're different depending upon how much this angle rotates them. So that's our goal for tonight, is to establish a way so that we can, if we know this, we should be able to know the stresses on any given rotation system. And the reason why this may be important is from the equations that we've learned so far, where you have the normal stress is equal to P over A plus or minus my over I. That gives you normal stresses. And tau is equal to VQ over IB. That gives you shearing stresses. But you may have a material that is sensitive to tensile stresses maybe. And in this coordinate system, you don't see your worst tensile stresses. You have to rotate this system to capture the worst compression or the worst tensile stresses. That's why this can be important. Okay, so this is our transformed coordinate system. Here's our x and y, and here's our x prime, y prime. Okay, so I'm going to start with a formulation of stress transformation equations. We define a rotated area, delta A. So on this rotated coordinate system, I rotate my unit cube here, my square, and I am going to define the width of that square as delta A, which means it has some area coming in and out of the page as well. How much is not important at this point, but this surface right here represents a delta A. And if this is delta A, then the surface normal to my original x-axis is delta A cosine theta, and this surface, normal to my y-axis, thank you. Sorry, everybody, you get to meet my black lab who likes to bark at car horns. Yeah. Do we have any questions? Any questions so far other than my black lab? Okay. All right, moving on. So this surface is cosine theta times this surface. And this surface is sine theta times this surface. So that's where we are so far. So we can define the components of delta A as delta A sine theta and delta A cosine theta. Taking a free body diagram of our inner slice, we can find the forces on each of the three sides. So that little delta that we had has forces on all three sides. And I'll kind of go, let's go clockwise. But what we have is on the inclined surface, we have tau xy prime, which is this stress right here, times our delta A is the area. Remember, a force is a stress times an area. So the stress is tau xy prime, and the force is delta A, or the area is delta A. So the force is stress times area. Likewise, on this inclined surface, my normal stress is sigma x prime, as shown here, times delta A. So that's the forces on the inclined face. And then on my horizontal face, I have sigma y, which is not shown here, but my original sigma y was up and down, times this area was delta A sine theta. Similarly, I have tau yx times the area is delta A sine theta. I have my original sigma x in the x coordinate direction times delta A cosine theta. And lastly, my original tau xy on my delta A cosine theta. So you see what we're doing here is we have one system, one free body diagram that has the transformed normal stress, sigma x prime, the transformed shear stress, tau xy prime, and I also have my original sigma y, tau yx, and sigma x. So this free body diagram is relating my original stresses to my transformed stresses. Any questions so far?
I have a question.
Yes, please.
It's on the previous slide with the like purple lines, and you said that they were different surfaces, I think is what you said.
Yes.
Can you go over that again, how they're different surfaces, please?
Sure. Okay, so see the green square. Okay, so let's go back a little bit and remember that green square, go back a little bit, there. That green square was a cut through this green cube. So the vertical line that you saw, actually it was like that, wasn't it? And that, and that. So when I say this is a surface, that's because that line is cutting through this face right here. And all of this is a surface. So you're looking down on a plan view of this square. I'll change my color here. That's the square that you're looking down on. And when I say that this line right here, which may be this line right here, is a surface because it's cutting through this whole face right there. So you have a length and you have a height. That is an area. So if I go back, if I can go back, and I know I'll erase those in a second. But I go all the way back to here. Okay, so this box here is that cut right there through the cube. So every line of this box here is actually representing a surface. So when I did here, when I just kind of sectioned out the inner guts of this cube, remember that this line and this line is a cut through the side of something that's actually a three-dimensional surface. So delta A is this length here times the height of that cube. Does that help?
Yep, thank you.
Awesome. Okay. So yes, no, that's a great question. I want you to understand it's kind of hard to draw it all and keep it all in the same screen, but we are working in a three-dimensional world. We're just made a slice right through the middle of our cube and are just drawing lines like on the surface of that slice. And you'll see at the end that the delta A washes out. So you don't need to worry too much about what exactly is delta A. Right now, it's just kind of like a placeholder so that you can see the geometry and how everything's related to everything else. So we get back to here, and really, again, the delta A's, you'll see there's a delta A in every single term. So it's going to wash out. Okay, so now what we're going to do, and this is a little busy, this is a little hard to read through, so I'll try to explain it so it makes sense. But what we're going to do is we're going to sum all the forces in the x prime direction, which is this inclined rotated x prime axis. We're going to sum all the forces in x prime. We're going to sum all the forces in the y prime. And what we're going to do is end up having expressions that will relate the x coordinate system to the x prime coordinate system. That's our end goal. So if I sum all the forces here in the x prime direction, then what you're going to see is on this face, I have sigma x prime delta A, that's a force, minus, because this is going in the other direction, or no, I'm sorry, minus this guy. Okay, so let me do this. See this vector right here? It has a component in the x prime direction. So the force is tau xy delta A sine theta. That's what I have here, times cosine theta gives me the component of that vector in the x prime direction. Then I do this face, which is minus sigma y delta A sine theta. And again, it has a component in the x prime direction, so sine theta, minus tau xy delta A cosine theta, and this vector has a component in the x direction, so sine theta, minus sigma x delta A cosine theta, and it too has a component in this direction, which is the cosine theta. All of that equals 0. 1, 2, 3, 4, 5 terms. 1, 2, 3, 4, 5 terms. Why? I have 6 forces on here. Why am I missing a force? Anybody?
Can you calculate it using the like c squared equals a squared plus b squared?
Oh, not necessarily. What I was getting at is that I have 6 vectors on the screen, but I only added 5 vectors equal to 0. Why am I missing a vector? And the answer is this vector right here, this tau x y prime delta a, is exactly 90 degrees in the opposite plane as sigma x prime. So there is no component of this vector that's in this direction. That's why. So this guy has 0 component on something that's 90 degrees away from it. So this one dropped out for the sum the forces in the x prime direction. Any questions about that? Okay. So I can take all of this and whittle it down to something much more simple. Sigma x prime is equal to sigma x cosine squared theta, y, sigma y sine squared theta, tau xy 2 sine and cosine theta. The point is, I now have our new normal stress in terms of the original 3 force components. There's 3 components that were independent: stress in the x, stress in the y, and the shear stress. And of course, we have our angle theta. So that was the goal. Come up with a sigma x prime that is related to the original 3 forces and the angle of rotation. I can do the same, sum all the forces in the y prime. And here, I won't go through each one of them again, but what we're doing is every one of these vectors has a component in the y prime direction. So I'm taking each one of these forces times the component of it in the y prime direction. So tau x prime y prime delta a, this force here is 100% in the y prime direction. And each of the others has a component that's sine or cosine. And the sigma x prime delta a has 0 component in this direction because it's perpendicular. So there's my 5 components equal to 0. And I clean it up and I can solve for tau x prime y prime is equal to this expression here, which again are just in terms of sigma x, sigma y, tau xy, and theta. So if I simplify these using trig expressions, then I get these 3 expressions. These are the 3 expressions that we're going to use to solve for these problems. Again, I would in danger of being redundant, but you will notice that each one of these expressions only has 4 variables: sigma x, sigma y, tau xy, those are given by the problem, and theta, the angle of rotation. Okay, any questions about our findings? Okay, so let's
Explain
do
it
it
again. I didn't
Yes.
get that.
Oh, I'm sorry, go ahead.
I was wondering if you could explain like again like the findings or how we simplified it.
Okay. It was through this free body diagram
Okay.
and all 6 of these vectors that we summated all the forces in the x prime direction and all the forces in the y prime direction. And we got
Okay.
these expressions down here. That's just from adding all these components together.
Okay.
These 2 expressions are a little dirty, so we simplified them using trigonometric expressions. I didn't put the math on here, but suffice it to say that's where these came from, and these are the simplest form that we can express these on.
Okay. So it's just from simplification of all the formulas.
Yes, yes.
All right. Got it.
Okay. So if we move to example number 1, find the normal and the shear stress on the transformed section rotated 30 degrees positive. So here is our problem statement. For these problems, counterclockwise is positive. please make a note of that. Counterclockwise is positive. X is positive to the right, Y is positive up, and rotation is positive counterclockwise. So if I rotate my coordinate system 30 degrees positive, this is what it looks like. And usually these types of problems are going to give you sigma x, sigma y, and tau. And again, I didn't label all the vectors because if you know one of the shearing stresses, you know the other three. If you know the sigma y, you know the other sigma y. If you know sigma x, you know the other sigma x. So that this is all you need here to describe the problems. Is everybody clear about the problem statement? Okay. So in this case, I am reiterating, just in case anybody missed it, I'm reiterating what the problem, the stresses, the normal, two normal stresses and the shear stress are in the original coordinate system. So see, the arrows are pulling away from the element. They're in tension. So that's positive. So sigma x is a positive 40 megapascals. Sigma y is pushing into the element. That makes it negative. Compression is negative. So you have to catch this. We didn't write it. I didn't put minus 80 up here. You have to catch that if it is compressing the element, that is a negative stress. And again, tau, if it's going on the x normal, going in the vertical y or positive y direction, then that is a positive shearing stress. So the 30 in this case is positive. So then to find the transformed stress on the x prime axis, at this point it's basically, I hate to use this term, but plug and chug. You use the equation that we just gave you and you put in each component. Notice that the cosine and the sine were 2 theta. Theta is 30, so you're going to be taking the cosine of 2 times 30 or cosine 60. That's it. Make sure you don't miss that. Also, what I did here is I was very deliberate about the way I inputted these. The sigma y stress is minus 80. So if it is sigma x plus sigma y, I put the plus, I put the negative. If it is sigma x minus sigma y, I put the minus, I put the negative. I suggest you do that to keep these straight. So running through this, I get sigma x prime is 35.98 megapascals, positive. And sigma y, this is a very similar equation, but the equation for sigma y yields minus 75.98 megapascals. And tau x prime y prime is minus 36.96 megapascals. And that is correct, it is negative. By rotating this thing 30 degrees, it's gone from a positive 30 to a negative almost 37. Any questions on this example? Okay, example number 2. Let's find the stress on a face of section positioned at 40 degrees. So this is a different way to express the problem, and it could be a little tricky. Firstly, what is given to you is all of your 3 independent stresses. I have 5 KSI sigma x, I have positive 3 KSI sigma y, I have a positive 8 KSI tau xy. So those are all given. But what is this deal here where I have a section A at 40 degrees from the horizontal? Well, it's looking for the stresses on this face. So to find the stresses on this face, what we actually have to do is take the whole coordinate system and rotate X until it is normal to this face. Okay? So theta is not equal to 40 degrees. Theta is the rotation it takes to get X normal to this face. So we have to rotate X prime until normal to the desired plane, like so. So this is my rotated X prime. And as you can see, I have rotated it clockwise. So my theta is going to be negative. Okay, remember, if it rotates counterclockwise, it's positive. If it rotates clockwise, it is negative. This is a very easy way to get tripped up. You would think theta is positive 40. It's not, it's negative 50. Okay, so theta equals minus 50 is what it takes to orientate this axis normal to this face. Any questions before I move on?
Professor,
Yes.
the 50 is given or we
No.
can't?
No, the 50 was not given. What was given was the 40. Okay, but what is normal to this face is 90 degrees to this face, right? So you have 40 and the whole thing is 90. So 90 minus, let me draw on the screen. Let me make this a little clearer. So here's your angle. This angle here is 40. And your transformed axis, X prime, is here, normal to that face. This whole angle is 90 because it's normal. That's the definition of normal. So the whole angle is 90. So this angle is going to be 90 minus 40, which is 50. But it's not 50 because it's going clockwise. So it's minus 50. Does that help?
Yes, thank you so much.
Okay. Okay, so I wanted to touch on that because I know there's quite a few textbook problems, statements, examples that approach the problem like this. And it can be very confusing that you think that they're telling you that the angle is 40 when they're not. What they're telling you is that you need to rotate until you're normal, and that's actually minus 50, and that's a completely different angle from what you might at first glance think they're asking for. Okay, so everything else is very straightforward, but our theta is minus 50. So now what I do is I establish my 3 independent stresses. I have 5 KSI, it is positive because it's in tension. 3 KSI, positive because it's in tension. 8 KSI, positive because on the X face, it is in the Y direction. So all 3 are positive. So now I plug and chug. I put in my 5, I put in my 3, I put in my cosine 2 minus 50, sine of 2 minus 50. And I simplified this a little bit so that you can see this is cosine of minus 100, sine of minus 100. And my sigma x prime is minus 4.05 KSI. Now, isn't that interesting? At minus 50, and this is drawn to scale, by the way, so this really is 50 degrees. At the x prime axis, I've gone from positive 3, positive 5 to minus 4. This element is actually in compression along this direction here. And my shear stress, I put in all the values through the equation, and I get my shear stress is equal to minus 0.404 KSI along that face. So if I go back up to here, hopefully just to drive this point home, my normal stress in this direction was minus 4, and my shear stress in this direction was actually this way at minus 0.4. That's what we found from that example. Actually, minus 4 would be compression. Sorry, that would go that way. Okay, any questions? Oh, I forgot I drew that. How about that? So there's our answer right there. Except for that is wrong. That's 405, not 0.45. Never mind the typo. But that's what the answer to that problem is. Okay, so what I want to do now is to kind of give you a feeling of what happens as you're rotating this element around in the circle and how that changes your stresses as you're moving around in this circle. So that was at minus 50 degrees. Let's reevaluate at minus 30 degrees. So here's minus 30 degrees. I have all the same original stresses. And I find that sigma x prime is minus 2.4 and tau is 4.87 KSI. Again, this really just becomes plug and chug at this point. In fact, tip to the wise, when I was doing this presentation, I got tired of punching this into my calculator like 16,000 times. I just went to Excel and plugged in these equations in Excel, and I made sigma x, sigma y, and tau xy as variables. And then they just plugged into these equations. And you can evaluate different angles a lot quicker that way. Let's reevaluate at minus 10 degrees. So there's minus 10 degrees. Same equations. And this time, notice everything is 2 times theta. Remember, the original equation is cosine 2 theta, sine 2 theta. So I get 2.2 KSI, 7.86 KSI shear. Reevaluate at 10 degrees. And there is a point to this, bear with me. So I reevaluate, I put in my 10 degrees here, 7.67 and 7.17 KSI. Reevaluate at 30 degrees, 11.4, 3.13. Okay, here's our final results. If I rotate that element minus 90 degrees, then my sigma x prime actually becomes what was sigma y prime. And doesn't that make sense? Sigma y was 90 degrees to sigma x. So if I rotate the whole thing 90 degrees, my sigma x becomes what was sigma y. And my tau becomes minus tau. At 70 degrees, at 50 degrees, minus 30 degrees, minus 10 degrees, 10 degrees, 30 degrees, 50 degrees, 70 degrees, 90 degrees. I think that was, yeah. Okay, so let's look at this trend here. As we rotated from minus 90 to 90, we basically went through the whole spectrum of all of the available stresses in the delta x direction. And actually somewhere right in here is 0. If you transformed it 0 degrees, this would be exactly 5 because that was the original problem statement, and this would be exactly 8 because that was the original problem statement. As you go through, it kind of is going down, down, kind of to like a minimum somewhere around here. Then it starts going up, 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 up to like a maximum somewhere around here, and then down again. So if you were to plot this, you'd see that it's kind of doing like a sine wave, going up and down. Same with the shear stress. which is just out of sync, but it starts at pretty much the lowest value, and it goes up, 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 kind of maximum around here someplace, and then starts going down to the minimum again. So you can see what happens as you start turning this and transforming it through this rotation. Anything more than 90 degrees is just repeating what's already happened. So between 180 degrees, you get the whole spectrum. Any questions so far? Am I going too fast with this topic? Okay. So you notice that the normal stress kind of maximized at a point, and then it started going back down again. And then there's a minimum point. So the maximum and minimum of the normal stress, this is the normal stress. So the minimum was right in here someplace, and the maximum was right in here someplace. Well, the exact minimum and maximum are known as the principal stresses. That's what the principal stress is. So there's a way to calculate without going through a million iterations exactly where and what, where being what angle and what being the magnitude of the principal stresses. And at the same time that you have reached your maximum or your minimum stresses, your shearing stresses will be 0. You don't see it here because we didn't hit the maximum right on the nose, but somewhere between these 2 points, the shearing stress is 0, and somewhere between these 2 points, the shearing stress is 0. So where you hit your principal stresses, at exactly the same point, you hit your 0 points of shearing stress. So from the last example, clearly there's a maximum and a minimum value for sigma x prime. To solve for the maximum and minimum values, the principal values, we first need to solve for the angle theta p where maximum and minimum values occur. We start with our equation for the transformed normal stress. This is just a repeat of what I had a few slides ago. And then everybody's favorite, we differentiate this with respect to theta, and we set that equal to 0. So the differential of this with respect to theta is this, where you have d sigma x prime over d theta equal to this, and we set that equal to 0, and we solve for theta. So theta p, the subscript p, just designates those 2 angles that correspond to the principal stresses. You actually have a theta p1 and a theta p2 that are separated by 90 degrees. So one of these is going to be the maximum normal stress, one of these is going to be the minimum normal stress, and they will be exactly 90 degrees apart. Everybody okay? It's awfully quiet out there. I hope I'm not talking to my blank screen. All right, forging ahead. If we substitute back into our equation for the transformed normal stress, we get our equations for the principal stresses sigma 1, sigma 2. So in other words, we take this theta here, and we take this lump and shove it back into this equation for theta, then we can solve for this. So sigma 1, sigma 2 is equal to, really, this is the average sigma. Sigma x plus sigma y over 2 is the average sigma plus or minus the square root sigma x minus sigma y over 2 squared plus tau xy squared. This plus or minus is what gives you your minimum or your maximum. At each principal angle, theta P1, theta P2, your shear stress will equal exactly 0, as I mentioned. Okay, so solving, this was example 2. If we solve for our principal angles, theta P1, theta P2, I'm using all the same values. This is a continuation of example 2. So I got my 8 KSI, 5 KSI, 3 KSI, and I run this, that equals 8. So I need to solve inverse tangent. So I use inverse tangent of 8 and then divide by 2. And I get theta P1 is 41.44 degrees. Theta P2 is going to be 41.44 minus 90. Remember, they're separated by 90 degrees. That gives me minus 48.56. The value of sigma 1 is my average stress plus this underneath the radical is 12.062 KSI. And my minimum is my average minus all of this under the radical, which is minus 4.062 KSI. And at the same angles, 41 and minus 48, tau is equal to 0. So here's the cool part. These we found by going through the laborious equations and plugging and chugging at each one of these angles. But now I can pop in here, minus 48.56 is giving me my minimum principal stress of minus 4.062. That goes here, and my tau is equal to 0. So this is where that fits in. You kind of intuitively knew it was going to be in this area somewhere, but now we have an exact number and the exact minimum stress for sigma x prime. Similarly, I can take my 41.44, pop it in here, and there's my maximum normal stress. And you can see it fits right in between the two. And you can see that my shearing stress at the same angle is equal to 0, which fits right between these two values. So everything jives. So this is kind of a more complete picture of the oscillation of the normal stress as you rotate that element. Any questions here? Okay. By the same token, we can find a maximum shear stress and our average normal stress. So from our example, you can clearly see that there was also a maximum and minimum value for tau, which is our shearing stress, which is minus 8 to almost 8 to minus 8. So there's going to be a minimum and there's going to be a maximum in here somewhere. To solve for the maximum minimum values of shear, we need to first solve for the angle theta s, where shear is maximum. We start with our equation for the transformed shear stress. We differentiate this with respect to theta and set equal to 0. And I didn't go through the same math, but basically what you end up with is tangent of 2 theta s is equal to sigma x minus sigma y over 2 negative over tau xy. The solution has 2 roots, sigma s1, sigma s2, separated by 90 degrees. Substituting back into our equation for transformed shear stress, we get our equations for tau xy. Tau max is at the square root of sigma x minus sigma y over 2 squared plus tau xy squared. And at each angle of maximum shear stress, the normal stress will equal the average of sigma x and sigma y. Which is equal to sigma x plus sigma y over 2. Okay, so back to our example. I can put in our values here for sigma x and sigma y over tau. and I solve for my angle. You put this in your calculator, and theta S will be, let's see, I think it was twice this. And then you divide by 2 to get to minus 3.56. And then add 90 degrees. They're separated by 90 degrees. So the other is at 86.44. And we can solve now for our tau max is 8.062. And our average is 5 plus 3 over 2 is 4. And guess what? We can put these into our study. So there's our minus 3.56. There's my average stress right there. Normal stress fits right in between there. And that's my peak maximum shear stress. Similarly, I can put in 86.44 into here, and I get my 4 KSI, and my minimum shearing stress is minus, you know what, I think this should have a plus or minus right there. Maybe everybody's homework is to check their textbook and see if this is supposed to have a plus or minus in front of the radical.
Looking
Seems-
at the textbook right now, it doesn't have one.
Didn't
It
you
does.
say earlier that the plus and minus was what made it be maximum minimum?
Yeah. Yeah. Well, if you take, that's interesting. Let me back up a little bit. This is the equation here for tau x prime y prime. So if you put in minus 3, you get the positive 8. If you put in the 86, you get minus. I think it works in here. So if you plug in these two values, you'll get positive 8.062 and negative 8.062. But here's where they fit in, right here. Obviously, between minus 6 and minus 8, that's where your minus 8.062 is going to fit in. So this is kind of the whole picture for that example, where we've gone from minus 90 to 90. We have found the minimum normal stress, the maximum normal stress, the minimum shear stress, and the maximum shear stress. Ooh. That threw me for a loop. I think that was my last slide. It was. How about that? Okay. How do I, okay, let me wrap this up in a nice tidy ball. And how do I do that? Let me see if I can get out of this. There we go. And let's go all the way up to here. Right there. Okay. So for example 2, we started with 5 KSI, 3 KSI, and 8 KSI shear stress. And when we rotated it through various angles, we got different values for sigma x prime, sigma y prime, and tau x y prime. And when we rotated it kind of through the whole spectrum from minus 90 to positive 90, we're then able to locate where the maximum compressive stress is, the maximum tensile stress is, and the maximum and minimum shear stresses are. And so again, I kind of get back to, okay, so what? What's the big deal? Why is that important to engineers? And so if I go back to the very last slide where we have this whole presentation of all these. Okay, so let's think of some materials. Let's think of a material like concrete. And let's say that concrete is really good at compression, but it's really, really lousy at tension. So you may have a concrete element rotated in such a way that you have virtually no tension, and you only have compression and shear. And I say, great, I have no tension. This material is going to be just fine. But what's going to happen is the material always finds its own weak link. So it's going to find the rotation of the coordinate axes where the tensile stress is maximized. So the concrete is going to naturally find right there at 41.44 degrees this maximum tensile force of 12.062 KSI. Okay, so if I can kind of draw this here. So what that means is that the concrete rotates, it kind of like rotates itself to maximize the tensile stress. And what happens when you put concrete in under tensile stress? What does it do? Okay, there's 28 people on this phone call. Somebody knows what concrete does when you put it into tension. Fails, there you go. That's what I'm looking for. It cracks. You put concrete in tension and it cracks. So this is all very important because you could have on your coordinate axes, everything is looking good. But when you rotate these axes, like the material will just naturally on its own, it always finds the path of least resistance. It's going to find its own path of least resistance right here at 41.44 degrees. It has this maximum tensile stress. If I didn't know how to evaluate this, if I didn't know how to transform these stresses, I, the engineer, would not be aware of this maximum tensile stress that I had better be, I better have known about, because I know my concrete is very weak in that direction. So that's why that would have been important. Another example, I could have a material where I could actually have, say, tensile stress, compression stress, tensile stress, and no shear. And I think, okay, if I'm talking about wood, wood is very, very weak in horizontal shear. So in shear in the vertical direction is no problem, but shear in the horizontal direction, it's very weak. I could look at this problem and say, oh, wait, no problem. I have no horizontal shearing stress, so no problem. But as you do this evaluation, you rotate it through all the possible directions of loading, and you'll discover that there are places where you have a maximum and a minimum shearing stress. And that might be the weak point for this material. Just because the material has stresses on our convenient horizontal and vertical axes doesn't mean it doesn't have very high stresses on some other direction. Does that make sense? Does that make sense of what's the point of all this? Why are we looking at all this? Okay. What we're going to do next time, this was the mathematical summation. In this episode of your Netflix show here, in this episode, we talked about the derivation of transforming stresses. We talked about how to find the transformed stress, and we talked about how to find the maximums and minimums of those transformed stresses. And we ran through an example with a lot of numerical numbers to kind of drive it home. Next time that we meet, we're going to talk about a graphical method to look at these stresses. You notice that there's a pattern to all this, and it turns out that a graphical representation of a circle illustrates these stresses in a very visual way. So we're going to do that next time. So that really concludes what I wanted to present tonight. We still have 8 minutes left. I'll just open it up if anybody wants to ask any other questions about anything.
So I have a question. So like to have like a table like that with so many angles though, like what was my question? It's like which of those values would you say is like generally like desirable, so to say?
It's not so much which one of those are desirable because you don't get to choose.
Okay.
The material is feeling these stresses continuously.
Okay.
So in other words, let me put it this way. If you load a material in such a way, by external loading, your my over I, VQ over IB, if you load the material so that a little element of that material is feeling this, oops, that one's backwards, but anyway, you get the idea. So our analysis, my over I, VQ over IB, all that gives us is a stress in the X direction, a stress maybe in the Y direction, and a shearing stress in the X or Y directions. But these are of our reckoning. We made these up. Which direction is X is our prerogative. Which way is Y is arbitrary. The material doesn't care if you considered horizontal X and vertical Y. The material is feeling stress in every direction.
Okay.
There's a spectrum of stresses all the way around here that the material is feeling all the time. So the material, we only, our limited ability to visualize this, we're thinking in X, Y, and shear. But the material is thinking that it's feeling this stuff all the time in every direction to varying magnitudes.
All right.
And then whichever direction that the material is weakest in, and that's just a function of the material, but whichever direction that the material is just not feeling it, that's the direction the material will fail at.
Okay. So like going for these calculations is a way of like determining like an analysis and stuff like that, and determining like at which angle like the material is weak at basically, and it has like and it's experiencing the most stress right there, and it can cause failure.
Yes.
Is that essentially what
Yes, it is.
the purpose
Now,
is?
to be honest with you, I'm a structural engineer. I design steel, I design wood, I design concrete. I do not do this in my everyday practice.
Okay.
That's not what this is not something that you would do in your everyday practice. But this class and all of these techniques and tools are foundational. And here's an example. If I design a concrete beam and I design it to the code and I follow all the rules and all the procedures, and they build this beam and they pour it and they put it in place, and then I get a phone call that says, hey buddy, you need to come out and look at this beam. And I come out and I look at this beam and I see these cracks that look like this. Okay, well, part of my knowledge, part of my understanding of, wow, what happened? What am I looking at? Is my understanding of these principles. And these principles are telling me that concrete is weakest in tension. That is its weakest direction. So that tells me that the principal tensile stress is in this direction. And the principal compressive stress is 90 degrees or opposite in that direction. So all of this is foundational to understanding stuff that you have yet to learn in your design classes and so on and so forth. That this is just basic mechanical understanding of what the material is doing.
All right. Thanks. Appreciate it.
No problemo. Anybody else? Any questions? Okay, Kelly has an interesting question. Since this example is on a small cube of a larger element, can the normal and shear equations we found today be used for virtually any similar solid beam? Kelly, I hope you're still on the line. I might have to ask a little clarification. But hopefully, let me start with this. Maybe this will help. Your equation for normal stress is my over I. So if I pull the cube out of here, then that cube is going to have a lot of compression on it from the my over I equations. But if I pull a cube out of here at the bottom, that cube is my over I is going to create a lot of tension in that cube down there. And this cube is near the center of the beam, so it has a little itty bitty shear on it. But if I pull a cube over here towards the end and in the middle, then that cube towards the end is going to have big shear on it, and basically no normal stress because it's at the middle of the center of gravity. So my over I is 0, and it might have a little compression on the cube from the loads kind of making their way down into the bearing here. So I hope I'm answering your question. These little cubes in different areas have different sets of sigma x, sigma y, and tau just based on where they are in the beam, how high or low they are on the beam, and what the loading is on the beam. Did that answer your question, or were you asking for something else?
No, that answers it. Thank you.
Perfect. Okay. Anybody else? The literally last minute question? Okay, thank you, Ryan. Very good. There's a few of you, hopefully you're still on the line. Everybody, please check with Blackboard and you can get your midterm score. I think we're still working on how you can get through Respondus to see all of my notes, because every single person, and I'm saying all this because some of you came in late, but every single person's test, I wrote down in each text box exactly why I took points away for that problem statement. So please try to go through Respondus and find those notes that I put on each person's midterm. That would really be tragic if all of that was lost, because it explains why you missed points, and that's very important to this. Also, there were a few of you who I didn't get a midterm at all. I think there was 3 students that I did not get a midterm. If you're one of those 3, you better get a hold of me, please. And also, like on the first midterm, if you scored, I want to say below 25, below 20, somewhere in that range or below, please get with me on a one-on-one basis. You can get me in my office hour or email me and we can find another time. But please get with me now. There are a few who are in, well, a position that we need to talk about. And that's all I'll say. I just don't want any surprises as we're finishing up this semester. For everybody else, thank you very much. This was recorded, so as soon as I log out here, I will put the recording up for everybody. Thank you, everybody, and we'll see you on Wednesday.